Hello everyone, I'm Hani, and today I'm going to explain the principle of pipelining that is applied to computer processors. The main objective of this video is to answer the question, how does instruction pipelining enhance processor performance? And we're going to answer that by gradually building a RISC-V pipeline data path. The motivation behind using a pipeline processor over a simple single-cycle processor is because single-cycle data paths are slow, because all instructions execute in a single clock cycle and thus the clock cycle time must be long enough to accommodate the longest instruction. Moreover, they are expensive due to the need to duplicate hardware resources such as adders, since each data path element can only be used once. A more efficient implementation is a pipeline processor, which can achieve a higher throughput by overlapping the execution of multiple instructions. A great analogy to understand how pipelining is more efficient than a single-cycle processor is to look at the way we do laundry. Assuming each computer instruction is analogous to one batch of laundry, which consists of 4 steps, a single-cycled data path would execute 4 steps, for example, in a manner similar to this. It would wait for each instruction to finish before starting with the next instruction. A pipeline processor, on the other hand, would make use of the fact that the task is made of several subtasks, and thus aims to keep every subtask busy by overlapping the laundry loads, that is, the computer instructions. However, in order to implement pipelining, we would need to modify our single-cycle data path. First, we need to divide our data path into 5 zones, which are the instruction fetch stage, which increments the program counter and fetches the corresponding instruction from memory, the instruction decode stage, which uses the corresponding bits of the instruction to read the operands from the registers and generates the needed control signals, but are not seen here. An immediate generation unit is also available to sign extend any immediate value that would be present in an add immediate or branch instruction, for example. We also have the execution stage, which performs the actual execution based on control signals. If an instruction is a branch instruction, it would use the adder to calculate the branch target address by adding the program counter to the immediate offset, and the ALU to resolve if the branch should be taken or not. We also have a memory access stage, which reads or writes data to memory if needed. And finally, the write back stage, which takes the data from the memory stage if it has been used, or directly from the ALU and sends it back to the registers using a multiplexer. However, in order for these stages to be independent, we need to insert registers to create physical barriers between the different parts of the data path. These registers would pass the results of one stage to the next. The control signals generated in the instruction decode stage would propagate along the data path in bundles until they reach the stage where they are needed. These data path registers move from one stage to the next on every clock cycle, with the clock cycle time being determined by the slowest execution stage. This means that the clock cycle time of a pipeline is much smaller than that of a single cycle data path, which is determined by the longest time an instruction needs to execute. While a single cycle data path always has a CPI of 1, a pipeline achieves that in an ideal situation only. This is due to hazards, which prevent the pipeline from operating at full efficiency. The first type of hazard, called a structural hazard, arises due to conflict between different instructions trying to access the same piece of hardware. The solution can be handled through hardware only and is the use of 2 physically different memory blocks, an instruction memory and the data memory. This would eliminate any hazard when the instruction fetch and memory stages overlap. The second type of hazard is called the data hazard and arises when the processor uses the wrong value of a register due to dependencies between instructions. There are multiple ways to solve this. We can solve it through software by either reordering the assembly instructions or inserting no-op instructions, but it is not very practical nor efficient. We can also solve it through physically stalling the pipeline until the result is ready to use. This, however, increases the CPI significantly and is not efficient. We can also use data forwarding, which is the best approach in fact. A small side note is that instructions in the pipeline read data in the second half of the clock cycle and write data in the first half, making it possible for an instruction in the decode stage to read the correct registers that have just been written in the write-back stage of another instruction in the same clock cycle. This, however, does not solve a dependency between an instruction in the execute stage and another in the memory or write-back stage. And to solve that, we add a data forwarding unit that detects the data hazard and forwards the result of a previous stage to the ALU. It does so by comparing the operands of the IDEX pipeline register to the destination register of the previous instruction in the memory or write-back stage. It also checks for special cases to make sure that forwarding is necessary. Unfortunately, not all data hazards can be eliminated by data forwarding. For example, if an instruction is in the ID stage and there is a dependency with the load instruction in the execute stage, we inevitably have to stall the pipeline by one clock cycle because the data is not yet available. This is detected by a hazard detection unit, which stalls the pipeline when needed. And stalling effectively means stopping the next instruction from advancing. This is done by freezing the contents of the program counter, injecting a hardwired 0 into the IFID register, and clearing all the control signals in the execute, memory, and write-back stages. The third type of hazard is called a control hazard and occurs when we have a branch instruction. This is a problem because instructions can enter the pipeline when in fact they do not need to be executed due to a branch. Up until now, we have been waiting for the memory stage to resolve the branch, which can result in a loss of 3 clock cycles. A slight modification can be done to resolve the branch in the decode stage and achieve a branch penalty of 1 clock cycle. This includes moving the branch adder from the execute stage to the ID stage and adding a comparator to check for inequality in the decode stage. A static or dynamic branch predictor can then be used to predict the outcome of the branch and fetch the subsequent instruction accordingly. In the worst case, the prediction could be wrong and the hazard detection unit would be responsible to flush the pipeline. To better consolidate the concept of pipelining, let us take a look at the following code. So what we have here is a loop that is going to execute for 100 times. Each time through the loop, we are going to load the value from an array and we're going to interpret this value as an address or a pointer to some location in memory. If this pointer is non-zero, meaning it has a legitimate address, then we're going to assign to this address a value that we're going to increment for each legitimate value we find. At the end, we're going to have a counter that stores the total number of non-zero addresses we found, as well as having assigned each of these addresses an integer. We will assume that the base address of my pointers array is stored in register x3. So there are a number of ways that this code can be converted into RISC-V assembly language. One way is the following, and of primary interest are these instructions that are going to make up the loop and get executed repetitively. Feel free to pause the video if you'd like to have a closer look at the code. We will assume a pipeline data path with data forwarding, hazard detection, and early branch support. Within this code, there are two branches, which lead to three different cases. The first case is when neither of the branches are taken. The second is when the second branch is taken but the first is not. And the final case is when the first branch is taken, exiting the whole loop. For the sake of time, I will only consider the case where the first branch is not taken but the second is indeed taken. The first two instructions get executed normally in the pipeline, but then we can see that we have a dependency between the add and the load word instruction, but in this case the dependency will be taken care of by forwarding, so we don't have to stall. We then have a dependency between the load word for x6 and the branch instruction. The value of x6 in the load word will not be available until the end of the memory stage, but the branch will need the value of x6 in the decode stage because it supports early branching. So the hazard detection unit will need to stall the pipeline for 2 clock cycles. There is also another dependency between the load word and the store word, but that will be taken care of by forwarding. And if we assume that the branch is indeed taken, the pipeline would not know that until the end of the decode stage of the branch. So the store word would need to be flushed by the hazard detection unit. We would then branch and execute the following 3 instructions normally. The instruction after the jump will also start executing, but the branch will be resolved in the decode stage, and thus the add would need to be flushed. And during that same cycle, the first instruction of the loop will be fetched again. Thus, if we were to calculate the CPI for this case of the loop, we would get 11 cycles per 7 executed instructions, giving us a CPI of 1.57. Thank you for watching.